Everyone. So previously we started doing some calculations on neutrino cross sections, specifically with quarks. But as you see, we have this neutrino to quark scattering cross section over the neutrino, the anti-neutrino to quark cross section, and we found this. Well, since this is the top one, we found a factor of 3 between the two. But experimentally, right, we saw that, well, the factor is actually more like 2 instead. So why is that? Okay. And so this has to do with the fact that you don't actually get to scatter things off quarks. You actually have to scatter them off nucleons, right? So nucleons are composite things made of multiple quarks, and some little bit of anti-quark in there also. So you actually have a different cross-section due to the structure of the protons and neutrons that you're actually scattering these neutrino off of. Okay, so now let's talk about this first neutrino experiment called CDHS is a very creative acronym. It stands for CERN, Dartmouth, Heidelberg, Scala. So these are just like the different institutions that are involved in building this experiment. It's actually physically located at CERN because that's where we have an accelerator. This is a little cartoon of the experiment itself. So you have a beam of neutrino coming in. Okay. So I think last time we talked about how we can actually create beams of neutrinos. Okay. And this beam of neutrino hits basically iron, which is made of protons and neutrons, and the protons and neutrons are made of quarks, right? In this little interaction, what happened is that then you'll have a shower. Basically, what happened is that the neutrino comes in, right? Let's say it's scattering off a proton, right? And this exchange between them, so this will be neutrino, so this has to be maybe actually in this case they're making muons, right? Okay, you have W minus here, right? This basically breaks the proton apart into some number of particles, right? And these particles are strongly interacting because there's these quarks inside a proton, and this is what makes this hadronic shower here. Okay, let me do that in red. It's better coloring, right? This hadronic shower has to do with this proton or neutron breaking up. Okay, but in addition to that, what you get is that you get a muon coming out of this, and this muon is going to pass through two different magnetic fields. So since the muon is going this way, magnetic field V cross B, right? So if you wanted to go down, you have a magnetic field going this way. And then in the other part of the chamber, you actually have a magnetic field going the opposite way. So it actually curves down and then curves back up. Okay. And there's all these electronics, ADCs and stuff like that, that if you were to work on an experiment, you will get to learn what all these things do in order to collect the data so that we can actually analyze in a little computer what we get as the result. Okay. And this won the Nobel Prize for Jack Steinberger and Leon Lederman and Melvin Schwartz in 1988 for basically the first actual measurements of a muon neutrino. Okay, so schematically coming out of this picture here, this detector here, there's a little mouse here also, I didn't even realize that. Yeah, it's about 1,500 tons of iron. Schematic what's happening is that you have a neutrino come in, make this hadronic shower, right? And then you have a muon that comes out at the tail end of that hadronic shower. And then you basically bend this in the magnetic field in different directions. And the reason you're bending is because, right, the curvature of bending, I forgot what that name is, but this is from the intro physics class, right? The radius of curvature from this when this charged particle in the magnetic field, right? You can relate that since you know the mass of the electron, you actually know the momentum. Okay, so you know actually how fast it's going. Okay, so you get the momentum of the muon, and then this X here, this hadronic shower, is also measured inside this lead target. Okay, by measuring what happens with the amount of energy that's collected at the end of the lead target. And so what you do, you get two signals. You get one signal for the hadronic part, okay, shower, okay. Let's zoom in a little bit more here. Then you have a track for the muon, okay. So in this case, right, so the mass of the muon is fairly low. You can actually measure both the energy of the muon and the energy of the hadronic shower. And then, surprise, surprise, if you add both of those up, right, just go up here, right, if you add both of those up, right, the proton started off at rest, so it's basically whatever the energy of the muon is and the energy of this shower is, right, tells you the energy of the neutrino, which is great. Okay, so this is an extremely cool experiment, okay. Knowing the energy of the muon, the shower, and also the neutrino, what that allows us to do is allows us to calculate this Lorentz invariant. In this case, we're going to use Y because it's just a little bit more convenient. Yes, you will see in a second, which is basically the dot product between P2 and Q and then P2 dot P1. Okay, so let's make sure we know what P2 and P1 is. Okay, so you have your neutrino coming in, right? That's P1, right? And your proton coming in, proton or neutron, whatever it is, it's actually a nucleon. They actually don't care which one it is. Okay, that's considered P2. Okay, even though, so we're going to use this in the rest frame. And then you have a bunch of stuff coming out. That's P4. And then you have P3 coming out. And then you have the Q, right? So Q can be calculated by just P3 minus P1. Okay, and then P2 is basically going to be, right, the mass of the nucleon at rest, right? Pretty simple. Okay, so you plug in all these momentums, right, with and do this dot product between them. What you'll find is that this Y is actually just come out to be the energy of the hadronic shower, right? And then divided by the energy of the hadronic shower, well, divided by the energy of the neutrino, but then the energy of the neutrino is just the sum of the muon and hadronic shower energy. Okay, so this allows us to convert things into Y, well, measure things in an experiment that tells us exactly what this, I think, remember, this is called the inelasticity parameter, right? Okay, so in the previous section, we calculated things in terms of theta, right? We found the cross section, the differential cross section for, let's say, the neutrino and the quark, right? Actually, the equation is so simple, even I can remember it. It's just 4 pi, GF squared pi S, right? Where S is the center mass energy. Okay, so we want to convert this to something in terms of Y instead, because Y, right, is a function of cosine theta, right? Okay, so how do we do this conversion? Okay, so if we put in the momentum for our little collision, so P1 is let's say we have a collision in general, so we have P1, you have a proton. So since this is all Lorentz invariant, we actually don't care which frame of reference we're going to calculate this in. P1, this is the neutrino. Say this is the proton, right, or neutron. Let's just call this a nucleon, right? And this thing comes out at an angle theta, so that's P3, right? That's your muon, right? And you just have a bunch of stuff coming out here that you actually, you'll only measure the energy of it, okay? What you find is that in general, what happened is that the relationship between this inelasticity parameter and cosine theta, dy d cosine theta is actually just -1/2. It's a pretty simple relationship, okay? In fact, y is actually just 1/2 1 minus cosine theta in the center mass frame. Okay, so that's nice. So if we start off, oh, did I forget this 4 pi here? Oops, 4 pi squared. Oh yeah, it's the total cross section that doesn't depend on that gets rid of that 4 pi because you're integrating. Okay. So what we can do is that we want to convert this to basically a differential cross section with respect to y instead of omega. Okay. So we know dy d cosine theta, which is -1/2. So what we can do is that, well, if we want d sigma dy, it's the same thing as d cosine theta dy, which is the reciprocal of this upside down, right, times d sigma d cosine theta, okay? And therefore, the relationship between d sigma d, let me just write this on the right-hand side, make it a little easier to read. The only difference between these two is this factor 2, okay? So therefore, right, if we want neutrino scattering, if you want to convert this in terms of y, d sigma d omega, right, that's the same thing as d sigma d phi d cosine theta, okay? And remember this, right, gives you a factor of 2, okay? So we actually have a factor of 2 here, 2 times d sigma d y, and you have this d phi. If you integrate out this d phi, you basically get a fact. Oops, this is actually 1/2, right? If you integrate out this d phi, what you end up with is a factor of 2 pi. Sorry. Okay. So in the conversion from d omega to d phi, okay, right? So basically, if you want d sigma dy, you just multiply 4 pi times d sigma d omega. Okay, so therefore d sigma d omega is actually going to be, remember this used to have a 4 pi square here, you just get rid of that, and then you have exactly that. Okay, so this is the differential cross section for neutrinos scattering into quarks. Okay, okay, so that's what this diagram is, right? You have a quark, exchange this, you have an electron coming out. So usually this will be, so this will be a W. So we have a positive charge here. So this is a negative charge, right? So 0 minus charge, then you get you have to have a W plus here. So going down, so there you have a +1 charge here. Therefore, it has to be a down quark that has a -1/3 going in here, giving you an up quark. Okay, that's how you figure that out. Okay, so from the charge conjugation symmetry, what you can do is actually just bar everything. Okay, so you have an E plus instead. Okay, right. You can do the same thing here. D bar, U bar. Right now, these particles are running backward. Okay, so these two diagrams are exactly the same, and therefore their cross section is actually exactly the same. Okay, but of course, if you're scattering off a nucleon, protons or neutrons, mostly you're going to be scattering off quarks as opposed to antiquarks, because the antiquarks are actually just from this gluon C, right? They don't actually they come in out of existence from the gluon as opposed to being permanently there, like the 2 up quarks and 1 down quarks that you have with the proton. Okay, we can do the same thing with the anti-neutrino quark scattering. So be a little careful, right? This is the anti-neutrino as opposed to scattering off anti-quarks. It's just scattering off regular quarks, right? So this diagram is actually like this, right? You have the same thing up top, but you have a U and a D going this way. Okay, so this is a anti-neutrino scattering off regular quarks, right? And we found that there's a factor of 1/3 between them, right? Because of this cosine square dependence. 1 plus cosine theta whole thing square dependence that you guys hopefully completed the homework on by the time you watch this. Okay. Luckily, right, what you can do is actually 1 minus y is actually equal to 1/2, 1 plus cosine theta. So you can actually just make the substitution in here, right? You have this, since we're squaring this, right, this is actually 1/4 1 plus cosine theta in the center of mass square, right? So therefore, you're actually replacing a factor of 4 down here also, okay? And remember the conversion from d omega to dy, there's a factor of 4 pi, right? Net, there's another factor of 4 and a pi that disappear from that. So when you calculate the differential cross-section of antineutrinos to regular quarks, right, as a function of this dependency on the inelasticity parameter, all you get is this G Fermi divided by pi, and then 1 minus y squared, of course, because you kept that. And then you still have the center of mass energy, which is 4e squared, right? That's what that is. Okay. So let's see if we can see this in data, right? So for neutrino quark scattering, right, you basically have no y dependence explicitly. It doesn't depend on y at all. For antineutrino quark scattering, you have this 1 minus y squared thing, right? So it's like an upside down parabola that's shifted, okay, because that's what y squared looks like. So let's see if we see this in the data, okay? So this is plotting, right, the differential cross section as a function of y, and then so this is the neutrino nucleon scattering. So you see that it's almost flat. It does go down a little bit as a function of y, and this is due to the fact that there's a slight dependence between the y and the q square. Okay, but for the antineutrino quark scattering, okay, right, you have this one. Basically, you have this parabola, right? Whoa, what's going on here? Right. So if you complete this, right, you have an actual parabola here. Okay. Right. And you can actually see this in the data, which is really cool. Okay. So this is how we can actually figure out how many neutrino will hit some nucleon, depending on what the nucleon is. So the bigger the nucleon, of course, the bigger the nucleus, the higher the Z or the A value, right? The more nucleons you have to scatter off of. So therefore, it actually increases your chance of hitting it, okay? And if you integrate out the this cross section, this inelasticity parameter, you can actually calculate what the total cross section is. So the total cross section, right, is just the sigma nu, the nucleon. We're not going to go through the calculation because I want to just kind of breeze through a little bit of this, because this is where we're going to get into a lot of minutia in the form factor for these nucleons. Right? Remember, these protons and neutrons are complicated things. What you get is that you're going to get this 1/3 factor between the neutrino to regular quark scattering and antineutrino to quark scattering part. Okay, so that's the fraction that we're dealing with. Okay, this is the same thing we saw with the when we're just modeling these quarks as just free spinners that you can actually scatter off of. Right, that's great. But the thing is, you have this contribution from the anti-quarks that's actually inside your protons and neutrons. Okay. Therefore, the ratio between the two is actually 3 times the fraction of quarks plus 1 times the fraction of anti-quarks that's inside your protons or neutrons, divided by the fraction of quarks plus 3 times the fraction of anti-quarks inside your protons and neutrons. Okay, you can basically see this from up here already if you do this ratio. Let's go all the way up here. Wait, did I skip that? Oh, yeah, it's over here. When we converted it. Yeah, you can basically see this already, right? Because when you swap the quark to anti-quark, you basically change things so that the anti-neutrino will scatter off of anti-quarks more, where the quark will, the neutrino will tend to scatter off the regular quark more. Okay, so if you measure this in data, this ratio in data, right, this is the same plot we showed before, right? You get a factor of 2 between them. Okay, and yeah, I think that this factor is almost 2. Okay, 1.984. Okay, right, and using the fact that your interaction cross-section between anti-neutrino to quarks divided by neutrino to quarks, you have this factor 1/3. You can actually measure the fraction of quarks inside your protons and neutrons, which is 0.41. You can do this little calculation, and then maybe we'll do a little homework to do that. Okay, and then the fraction of anti-quarks inside your proton, which is going to be about 8%. Okay, so you can actually figure out how much of your protons and neutrons are made of quarks, not just the valence quarks, the UUDs, but the valence quarks plus the C quarks that are also, you know, regular quarks, and then what fraction is it actually the anti-quark. Once again, notice that this number does not add up to 1. So a lot of the momentum or the energy carried by protons and neutrons, in this case almost half, a little bit more than half, is actually carried by the gluon itself. Okay, so if we probe the so using neutrino, you can actually probe the internal structures of protons and neutrons also, yeah, through the weak force, just like the electron using when you use QED. So this takes us to another experiment called NewTeV. This is actually a experiment that measures neutrinos at the tevotron. So the tevotron is actually an accelerator that used to run at Fermilab. And what they do is they basically use the fact that you can get to this ratio, the difference in how the neutrino interacts with quarks versus the neutrino interacting with the anti-quarks. You can actually get these structure functions from these experiments. Okay, and so here, this is where we're doing the fraction of neutrino to nucleon. So that's this line here, right? Okay, so that's just that's another form factor how much the neutrino interacts with the quark, and then you have x times that, and that's where this graph comes from. And notice that this is very similar to basically what x times the fraction of up quarks looks like when we did the QCD chapter. Right. You can also probe the structure of the protons. Well, in this case, only protons, because we're talking about Hera, which is actually smashing the electrons and protons together. You can do this without measuring the neutrino itself. And how do we do that? So, for example, in this experiment, I think it's the H1 experiment, which is on the right-hand side here, if I remember right. You have a collider that's smashing, oops, let's do that in red, that's smashing electrons and protons together, right? And then when you smash them together, you measure what comes out. So in the H1 experiment, so I think this will be the proton beam, this will be the electron beam. Okay, what happens is that, well, you have a bunch of stuff coming out. So this is, the hadronic stuff that comes out. And let's say this event made a mu plus, mu minus. Okay, right? So that doesn't tell you, oh, where did the neutrino go, right? The neutrino really passes through the detector without being detected. But if you look at maybe like the XY view, meaning looking down the beam pipe, okay, what you'll see is that, well, the muon came out this way, the mu plus came out this way, the mu minus came out this way, the hadronic stuff came out this way. It seems like, right, there's an imbalance of stuff coming here, right? So what you can do is that, so you can infer that this is actually where the neutrino come out of, okay? So this is, those of you working on the LHC, it's usually called missing momentum, right, or energy, depending on who you ask. Transfers. Okay, the reason it's called transfers is because you're looking at the missing momentum transfers to the plane of the collision. Okay, so these are called MET. Okay, and sometimes it's actually called ET with a slash. Okay, it's just missing, or PT slash or whatever. Okay. So using these experiments, you can also infer, right, the momentum of the neutrino that's coming out of these experiment, okay, the missing momentum. And if you have that, you can actually calculate the difference between what's known as a charge current, a neutral current versus a charge current. So the neutral current, right, it's basically you have an electron, and then you have an electron coming out, and then you have a photon with your up and up quarter. Okay, so this is neutral, right, because the photon has no charge. But then if you have this diagram instead, right, you have a different interaction. Okay, what you can do with this is you can actually measure the ratio between the electromagnetic coupling constant and the weak coupling constant. And you can actually see this here in this data set where we're plotting d sigma dq. So basically you're taking a differential of this, okay? And then you're plotting this dependency here. And then you can see that for the circles, which are these guys, right? This is the coupling through the neutral current through quantum electrodynamics. And then you can see that this is actually through the weak force, okay? And they have completely different shapes because, right, because this ratio between the alpha of the electromagnetism and the alpha from the weak interaction, okay? We're just going to talk about this a little bit more conceptually for now, okay, instead of diving into the calculations for it. So hopefully that's useful. It tells us how we actually measure these things in a neutrino experiment. And a lot of times when people say, oh, I'm going to go measure neutrino, this neutrino, that, you actually never really measure the neutrinos directly. You're always measuring the neutrinos scattering, hitting something, and then that something is actually what you measure. Okay, and that's all I want to cover in chapter 12 of Thomson. So next we're going to go to chapter 13 on neutrino oscillation and masses, and that'll give us a lot more calculations to do. Okay.